Institute, the College of Natural Sciences, the Jackson School of Geosciences, and the Longhorn Network, which will air their edited version of tonight's event, along with an interview with our speaker, on November 18th, noon to 1. That's a Sunday at noon. So right before the NFL starts, you'll get some last call at the Oasis. And as a reminder, please turn off all electronic devices. No talking during the lecture. No texting, no electronic anything. The program has a Q&A session. We're beginning at 7. We'll end at 8:15. So at the end of the talk tonight, the speaker is going to be saying thanks for coming, because that's for the Longhorn Network, but it's not for you guys. You guys are going to stay here because we're going to go right into the Q&A after you give the speaker your appreciation. So tonight we're going to hear about last call at the Oasis. Will there be enough water for the 21st century? And the speaker is Dr. Jay Famiglietti, who's a professor of Earth System Science at UC Irvine. And I'll give you a little bit of background about Jay. He's one of the leaders in looking at the interactions between climate and hydrology. He's a fellow of the American Geophysical Union, which is one of the most prestigious awards a scientist working in the field of earth sciences can achieve. He's currently squeezing us in on another honor he's received. He's the Birdsall Dreiss Lectureship Award winner for this year from the Geological Society of America. So something like 40 cities, 48 nights, something like that. I'm really happy that he could fit us into his schedule. And by way of background, Jay was born and raised in Rhode Island, in the town that's depicted on the show Family Guy, which some of you may be familiar with. He was an undergraduate at Tufts University, and he was on a track to be pre-vet or pre-med. And he was starting his sophomore year a little disillusioned with what he was doing, and he needed another course to fill out his schedule. His girlfriend at the time told him about this geology course she was taking and really liked. And it was 2 weeks into the semester. It was like the last day to drop ad, and he added this geology course, and he was so enthralled with it, it actually changed his career path. And he set off about studying geology and water, which he was just really fascinated with. He went on from Tufts University getting his degree in geology, but he was also formed even before going to college. He was formed by being a Boy Scout. He became an Eagle Scout, and it seemed like one week after another they were doing a project in which they were cleaning up water here, cleaning up water there. He became really inspired. He went on to do a PhD at Princeton University, got his degree in civil engineering, and then moved on to do a postdoctoral fellowship at the National Center for Atmospheric Research in Boulder, Colorado. And then we were fortunate enough to hire him here at the University of Texas to join the Department of Geological Sciences. But after about 10 years, the withering summers got to him, and he left for sunny but more moderate skies at the University of California at Irvine. And we're happy that he's returning to his Texas roots here tonight. Please welcome Professor Jay Famiglietti.
Thank you, Jay. Let me find my presentation. There's the trivia slides. I think you saw those already. So, good evening, everyone. I'm Jay Famiglietti. Welcome to Hot Science Cool Talks. It's great to be here. It's great to be back in Austin, as Jay said. I joined the faculty. Actually, I interviewed here 20 years ago. So it's great to be back. And the memories that I have of UT are quite fond, as I'll show you in just a second. First, I thought I would start off by changing my title, and I like the one that maybe Jay assigned it, maybe we picked it together, I don't even remember, but we picked it a while ago. It's called Last Call at the Oasis, Will There Be Enough Water for the 21st Century? And as I was putting the slides together this morning, I thought that this might be more appropriate, and you'll see why as we go through some of these slides. Last Call at the Oasis, is this our inconvenient truth? So think about that. We'll get back to that at the end of the presentation. Oh my gosh, look at how sweet that is. So the memories that my wife and I have of UT are extremely fond. Our kids were both born here. This is right out next to the geology building, next to the fountain. And this was on the day that we got this new puppy. He was 12 weeks old. His name was Gordy, and he turned out to be just a fantastic dog. We picked him up down in Buda, And the kids didn't turn out too badly either. My son is now a freshman in college, if you can believe that. If I can believe that, my daughter is a senior in high school. So my wife and I had a fantastic time here, and we miss it quite a bit. This is probably around 1998. So Jay mentioned, well, you know, movie star, that's kind of interesting. I haven't quit my day job. I had the good fortune to be involved as one of many experts in a movie called Last Call at the Oasis, which is actually played here in Austin a couple of times now. A fantastic production team. It was done by Participant Media, which is the same company behind Waiting for Superman, Food Inc., and An Inconvenient Truth. So I learned a lot about myself and a little bit about the movie business. I learned that I was delightfully glum. I learned that I was droll and deadpan. I don't know what they're talking about. I was humiliated then and even tonight by having makeup applied and being fully mic'd with the sound on while going to the bathroom. It's one of life's greatest adventures. So this is after one of the first filming sessions, and the team here includes Academy Award winner Jessica Yu, who is the director, and Academy Award nominee Elise Pearlstein, who was the producer. And so somewhat humiliated or disappointed to learn, well after the movie came out, the producer told me, well, we really didn't know who you were, so we sent out the B team to film you on that first day. And, okay, that's fine, another blow to the ego, no big deal. And they had people follow me around taking film of my feet. That was cool. The movie did play here. That was a lot of fun. I was here in March for South by Southwest. Let's start off. So what I'd like to do is show you a few clips from the movie, and most of them will introduce a research topic or a theme that I'll talk about for a little bit. We'll start off with the trailer to kind of set the stage for the movie.
Infinitely and inexhaustibly. But when you use water in such quantities that it exceeds the capacity of the system to renew itself, you have a problem.
Farms all over the Central Valley are allowed to dry up. The drought in China's southwest region is the worst of the last century.
4,000 children die each day because of water shortages, and the situation is worsening.
In the scientific community, we're starting to think it's not drought, it's really part of climate change.
We can't take it for granted that the chemical can pass through silter sand and on the other end come out pristine.
There is no future here because of the control of the water. They are gradually taking it away from farmers. It won't be good.
With the raw sewage being discharged into the River Jordan.
It's not one lake. It's not just one well that's contaminated. It's 30, it's 300, it's 3,000.
If we were smart, we would dramatically rethink agriculture and urban water use. Over the last decade or so, Singapore has worked very hard to develop new, innovative sources of water.
It was Albert Einstein who said, "Those who have the privilege to know have a duty to act."
There's a common agenda for all of us, for every walk of life, and that's why.
was dramatic. So that was the first version of the trailer. I got left on the cutting room floor after right when the movie came out. It's okay. It's just yet another blow. You know, it's a tough business. But you know, it's a good thing I'm a professor and not an actor, because I don't think I could sustain the multiple blows to the ego. I just want to say to the teachers that are here, one of the reasons why I participated in the filming of the documentary is that I think it's going to be a tremendous teaching tool. So hopefully, and you can check back with Jay on some of this, we'll be working at UC Irvine and developing teaching modules based on the different stories that are told in the movie, many of which were just shown there in the trailer in just a very, very short form. So please check back and think about using it, because I think it's really going to be a remarkable teaching tool. Okay, I'd like to launch into some of the research that we do and introduce it by a clip which I call My Big Screen Debut. And one of the, I think, funny things about being involved in documentary filming like this is that there are no do-overs. So you do it, and that's it. It's done. And there's a lot of editing for sure. So I was always quite nervous when I watched the film for the first couple of times. But again, I think I came through it okay. I'm still here, and I think the producer and the director did an excellent job. So the setup here is that I'll be talking about the Gravity Recovery and Climate Experiment, the GRACE mission that's actually based here at UT Austin. So let's watch this. Oh, sorry. So before, oh, wait, messed up. Here we go.
For many years, I've been working with a satellite called GRACE. If you are looking at an area that's had a big mass change, say from groundwater depletion, GRACE can see that because the mass change is so big that it's actually sensed by the satellites. We can see significant depletion in California. We've been keeping a close eye on the Central Valley. The view from the ground is muddied by the politics. The view from space is clear and undeniable. If we go back to 1998, the aquifer has lost about 1.5 times the volume of Lake Mead. That's a huge amount of water.
How much is left in the aquifer?
Let me see how I can sugarcoat this. You know, I ran some back of the envelope numbers, looking at how long it would take at those pumping rates for the aquifer to be depleted. And I got a number between, say, 60 and 100 years. So at the low end, 60 years, that's frightening. I think California is in trouble. The combination of climate change growth and groundwater depletion spells a train wreck.
Wow, equally dramatic. I think that's true, and it's not just California. I think that big chunks of Texas are facing that same future, and I'll show you some graphics later that show the southeastern part of the United States has also had a rough decade. So let me talk a little bit about this work that we did with the GRACE mission. And so I'd like to recognize first my PhD student, Matt Rodell, former PhD student from before it was the Jackson School of Geosciences, it was the geology department, was the Department of Geological Sciences. So Matt was my PhD student there roughly from 1995, 1996 to 2000. We continued to collaborate, do a lot of work together using the GRACE mission to track water storage and groundwater depletion changes all over the world. And here's a picture of us at last year's AGU meeting comparing at the time our Josh Beckett-inspired beards. So like supervisor, like student, I guess. And also I need to recognize, of course, that the GRACE mission is really based in large part here at UT Austin. That's Byron Tapley, the director of the Center for Space Research, is the principal investigator. And it's because of Byron and his colleagues like Clark Wilson in the Jackson School of Geosciences that I got involved. in using the GRACE mission and trained Matt into some of that research. And I've really been able to do a lot of really exciting things with the mission data in terms of tracking climate change impacts and human impacts on hydrology and water availability. Okay, so GRACE, it's a gravity mission. GRACE stands for Gravity Recovery and Climate Experiment. And it's actually 2 satellites that look sort of like this. I think I have a picture here for scale, right? You've got a couple of humans in there for scale, so you see that it's not, they're not very big. What this mission does is map Earth's gravity field. And this is a figure that shows Earth's gravity field, which is really controlled by the tectonic and the topographic features of the Earth, where the continents are, where the ocean trenches are, where the mountain ranges are, and so on. And so this shows our knowledge of the gravity field before GRACE, so it's pretty blotchy. And then this is what we get after GRACE. Okay, so we've gotten like this vast improvement in our understanding of the gravity field. Okay, we can sort of map it out onto a globe, look at it in 3 dimensions, and it looks something like this. Okay, what does this have to do with water? Really, with GRACE, we're making a map like this almost every month. And so imagine now, if we're looking at the United States, and imagine that a heavy load, a foot of snow, was dropped on the Rocky Mountains. There'd be more mass, there'd be a greater gravitational acceleration, and there'd be a different signal that GRACE would measure. So by looking at these monthly changes on land, we are primarily looking at changes in the water stored. Okay? So let me sort of repeat that. The difference between 2 GRACE global gravity fields, like these that I showed you here, imagine this one in January and then this one in February. The difference we call the time variable component. The main contributors to the time variations in the gravity field are changes in water. It's in the ocean, in the atmosphere, and on land. We're primarily concerned about the land tonight. And the reason is because water is super heavy, right? We know that from carrying a case of bottled water from the grocery store to the car, or in Costco or something like that. So we know how heavy it is. Or if you've ever shoveled snow, you know how heavy it is. So really, the time variable signal, these monthly differences that we see from the GRACE mission, are dominated by changes in what we call terrestrial or total water storage. That is, all of the water stored in a region. Okay? All of the surface water, all of the soil moisture, all of the groundwater, okay? All of the snow. So what GRACE, if we look over here in the upper right, and imagine that this is a big river basin like the Arkansas River Basin. GRACE would give us a monthly change in all of the water. Okay? It can't really tell us that this much is snow, this much is surface water, this much is groundwater. We need other data sets to do that, and I'll get to that in just a moment. It works for, it's not a panacea. It works for low spatial and temporal resolution, so monthly time scales and large areas, 150,000 square kilometers or greater. So it's not like a Landsat type satellite. It tells us more the longer-term monthly seasonal changes over a big region. Here's a time series for, I believe it's the Rio Grande, and it shows what the monthly data look like. So this is showing us the change, the ups and downs of water storage, how it's increasing, how it's decreasing. Every dot is a monthly value. The units here are millimeters of water, so it's a millimeter of water spread over the whole river basin. And it just shows how the storage goes up and down. And so it would go up because of precipitation, it would go down because of evaporation and stream flow, or drainage out of a region. And so you can see, the drought of the past few years, and especially over the past year, if you look towards the end of this time series, the end of this chart shows it really, really well. Okay, so that's a little background on GRACE. I think a take-home message, if there's one thing that I think I'd like you to remember, it's that GRACE is like a giant scale in the sky. It doesn't tell you how much you weigh. It doesn't tell you that you weigh 175 pounds. It tells you that you've gained a pound of water weight this month, and a pound the next month, and a pound the month after, and then maybe you start exercising and you lose a pound and you lose another pound. Okay, so think of it as a giant scale in the sky that's keeping track of how much water weight you're gaining or losing. Here's what some of the data look like. And you can see from this animation that the data are fairly coarse. They're fairly blobby. Each new image, each click here is a different month. And in this color scheme, the reds are wetter than average, and the blues are drier than average for the time period, which in this case is about 2004 to about 2010. So I think it's best to just focus on a region to really sort of take in what's going on here. If you just look at a region like the Amazon, you can watch it get drier, right? And now we're getting into the wet season, so it's getting wetter, so those reds come in. So we cycle through the blue, here come the blues, and then it's starting to get wetter, and now we're into the wet season, right? So we get this cycling of the wet and the dry seasons. And so we've been studying these data for a long time. We've been comparing them to observations on the ground. We've been comparing them to other satellite data. We've been comparing them to computer models. And they agree quite well with most of the information that we've been looking at. I want to take some time to talk about some examples of how we can isolate the signal of groundwater depletion from the GRACE data. It's something that we pioneered. We actually pioneered it here when we were at UT Austin with Matt and I together for part of his dissertation. And then as the length of the GRACE data period grew over time, we were able to test it out in a lot of different regions around the world. And as the data set lengthened, then trends, for example, in groundwater depletion began to emerge. So one of the things that we have to do, if we want to take this GRACE signal, which I mentioned gives us a monthly change, but it gives us the change in everything. It gives us the change in the total amount of snow and river water and soil moisture and groundwater. It doesn't say this much is groundwater. So GRACE, what GRACE is really telling us is this here. It's telling us this delta S land. But as a hydrologist, we know that that change in storage, delta S, for the land is actually composed of the change in storages of these main components of snow and surface water and soil moisture and groundwater. So all of these things, if we look in this figure, all add up to the total. If we want to isolate the groundwater signal, then we can move it over here to the left-hand side, rearrange the equation using some simple algebra. If we want to solve for this groundwater storage change, we want to find out basically from satellite how much groundwater is being depleted. We can take our GRACE signal, which is this delta S land, our GRACE data, and subtract from it the snow, the surface water, and the soil moisture. If we look at this chart here, this figure down in the lower left, GRACE is giving us the change in this total river basin. Again, imagine it's the Arkansas Red River Basin or something like that. If we want to isolate the blue stuff, the groundwater, we have to remove the snow, all of the mass change above it that GRACE sees. We have to pull it out. So we have to pull out the snow, the surface water, and the soil moisture. So we have to come up with data sets for these different variables. Again, the snow, the surface water, the soil moisture. And we do that by collecting data sets from the ground, from ground-based observations, okay, from other satellites, or from computer models. In some cases, we don't, for example, a case of soil moisture, the moisture in the upper few centimeters of the soil, we don't really have good measurements of that in the United States, so we have to rely on computer models. We've gone through this exercise a few times, and I want to show you some real highlights. One, in the movie, then we talked about the Central Valley. And the reason that the Central Valley is so important, well, there are a number of reasons why the Central Valley is important. It's one of the most productive agricultural regions in the world. You may not know it. I didn't know it when I left Austin, but I learned it pretty quickly after I moved to California. It's responsible for producing a number of different crops, a couple of hundred different varieties of crops, billions of dollars a year in food. It accounts for a sixth of all the irrigated land in the United States. The Central Valley Aquifer is the second most pumped aquifer after the High Plains or the Ogallala Aquifer system. We know that groundwater depletion has been going on there for some time. and subsidence of the land has been happening for some time. Here's a picture of a famous picture, actually, of a USGS scientist standing next to a well casing. This is the inside of a well. Okay? The land surface used to be way up here at the top, and because of all of the groundwater depletion, it's like letting air out of a tire, right? The ground actually deflates. All right? So we've known that it's been going on for some time, but it's difficult to quantify. And it's difficult to quantify with data on the ground. So what we have been able to pioneer with GRACE is a very complementary space-based approach that I think needs to be combined with the very important data sets that we have on the ground. So these charts over here on the right, really, these are just an expression of that exercise that I just explained to you, which is if we want to find out how much groundwater is being lost from a region, we have our GRACE data, which gives us the total. That's over here. And from it, we need to subtract what's not groundwater. So we subtract from the total the snow, the surface water, and the soil moisture. In this case, we get our snow data from the National Weather Service, the National Operational Hydrologic Remote Sensing Center. Our surface water storage data came from the Department of Water Resources in California. And for soil moisture, we use data from the NASA Global Land Data Assimilation System. So we take A and we subtract from it B, C, and D, and we end up with this chart, which shows groundwater depletion in California's Central Valley. And so each dot is a monthly value of how much water has been gained or lost from the groundwater. And if you look at the big picture here, we see an overall blue trend line, which shows that that region has lost, as I said in that clip, that region has lost about 20 cubic kilometers of groundwater, or 2/3 the volume of Lake Mead, most of it in a time period of about 4 or 5 years, which is shown by these broken red lines here. So what's happening in this first part of this data set here is that there's plenty of surface water available for the Central Valley farmers. But then a drought kicks in, a very big drought, like the drought that we're having here in Texas. And in that time frame, the farmers' surface water allocations come from snowmelt. They come from the snowmelt from the Sierras, the Sierra Nevada mountains. Their surface water allocation was cut, in some cases, by as much as 90%. So the farmers had no option but to use groundwater. And so they hit the groundwater pretty heavily, and the water table fell at a very, very rapid rate, and we can see that here with this second broken red line. We see that decline in the water table. So it's very interesting that we can pick this up and see this from satellite, and it's the kind of thing that I think is going to be very important for water management here in Texas. Here's an example of some GRACE data looking at this, at the whole state region, and so we see sort of the beginnings of the drought, big drought back in 2006, and then the slow, steady decline up until about the present. These are the GRACE data for that time period, and then here's some data from a local well. And you can see that the two, if you compare the red line to this bluish line here, they track each other quite well. So it works well, not just in California, not just in Texas, but really all over the world. If you follow global water issues, you know that one of the places that has the most significant groundwater depletion in the world is northwestern India, up here in this Punjab region. It's very much like California's Central Valley, a heavily agricultural region that relies quite a bit on groundwater. So we applied this method of taking the GRACE data and subtracting from it the surface water and the snow and the soil moisture, and we're left with these blue lines. The blue line is the monthly the solid blue line shows the monthly variations in groundwater storage changes, and the dashed blue line shows the overall trend. That's a trend of it amounts to about almost 110 cubic kilometers of groundwater over about a 6-year period. That's an incredibly rapid rate and unsustainable rate of groundwater depletion. And again, it's something like 3 times the volume of Lake Mead. So it's huge. It's also a resource that's shared with Pakistan, so there's the potential for conflict. Likewise, a paper that we're working on right now for the Middle East, centered over Turkey and Syria and Iran and Iraq. We see another, so the same process of taking GRACE data, assembling these supporting data sets of snow and surface water and soil moisture, removing them from the GRACE data and focusing on the residual, which is the groundwater. So to get to the punchline, here's our groundwater depletion chart for the Middle East. And that region, in about a 7-year time period, from about 2003 to 2010, has lost a total of about 150 cubic kilometers of groundwater, and about 2/3 of those, about 95 cubic kilometers, are from groundwater loss. So this is an area of great concern because, again, we're talking about transboundary aquifers in a region that has been historically prone to conflict. We'll be visiting this region and presenting some of these data in late January, early February, really wrapping up this lectureship that Professor Banner was mentioning. Okay, so here's the big picture of GRACE data. This is a map of the global trends. Okay, so in this figure, blue, areas that are colored blue are gaining water, and areas that are colored red are losing water. Okay, so some of the biggest red signals that are losing water are the ice sheets, Greenland and Antarctica, and after that, glaciers like Alaska and the Patagonian glaciers. Just about all these other red spots, as we look across the world, really, Australia, China, here's India, here's the Middle East, Southern Africa, Argentina, even the southeastern U.S. Most of these are related to groundwater depletion. Okay, so I think this figure really shows, and I'll highlight it a little bit more, really shows the fact that we've got this groundwater depletion going on, not just in California, not just in Texas, but really all over the world. It's something that I believe is unsustainable, and I think that the GRACE data will help us, ultimately help us manage this precious resource in a more sustainable way. This same figure, now I've just labeled some of these red spots. Okay, so we're seeing groundwater depletion in the North China Plain. Here's India, Bangladesh, even on the northern side of the Tibetan Plateau, the Himalayas, all across the Middle East, all across southern Europe. Here's the southeastern U.S., the high plains, California. This is drought in the Amazon. You can even start to see some of the Peruvian glaciers melting. The Argentina drought and the groundwater depletion, it's called the Guarani Aquifer. This signal way over here in northwestern Australia, we're pretty sure is related to mineral mining. The water use for mineral mining is quite huge. So it's showing up in our data set. So I'm concerned, and I hope that you are too. And the bad news doesn't stop there. So let's continue with we'll try to continue with another clip.
The whole nature of the water cycle is changing, driven by changing climate. In our new study, we found that the water cycle is intensifying. That truly means a much more stormy future in many parts of the world, and in other regions will have more extreme droughts. You know, what I think we have here is really a smoking gun for water cycle acceleration. When we string together some of these last few studies, these are first of their kind observations. There have been many studies that suggested that this may be happening in the future, and our research has shown this is actually happening right now.
The whole thing to me is just incredible. The fact that it's increasing or changing in time.
Will the water cycle spin out of control? It's hard in the United States to fathom the scope of the potential change, and the scope is huge.
These current findings, this is going to get people's attention.
I don't think so.
Let me stop it there.
Do you think that we have this right to use as much?
I'll stop it there because that's a nice segue into, are these wet areas getting wetter? Are these dry areas getting drier? Will we be experiencing more drought in regions like Texas and more flooding in high latitudes and in the tropics? This is a famous figure from the IPCC, the Intergovernmental Panel on Climate Change, fourth report from a few years back. And it shows the projected changes in precipitation by the end of the century in the winter, December, January, February, and in the summer, June, July, August. Again, by the end of the century, the reds are getting less precipitation, and the blues are getting more precipitation. So our climate models are predicting this mid-latitude drying. And you can see that Texas is sort of right on the fringe of that. And so the dry air is getting drier, and the higher and low latitude area is getting wetter. And so what do we see in the GRACE data? I've looked at these data for so long that I see lots of things. I mean, I see, the Madonna in here sometimes. But I do see a lot of reds and yellows in the mid-latitude, so I'll just put a box around that. And, you can tell me if you agree or not. I think there's a lot of red and yellow, which means losing water. Over this time frame, which is 2002 to 2010 in this particular figure. And I do see a lot of blue in high latitudes, and I do see a lot of blue in the tropics. And so I'll just ask the question, are we seeing this redistribution already? I don't know the answer, and of course more data will help answer any questions. But that's what's there right now. I just wanted to pose this question to the group, and it's one that I gave a presentation earlier today in the Jackson School, and made the case for using some of these data in water management. This is a blow-up now of the United States. And again, the red and yellow areas are losing water, and the blue areas are gaining water. And so I pulled out a few charts to show what's happening on a monthly basis for the Central Valley in California, which we kind of talked about this big drop here. Here's East Texas, big drop, see the big drought. And then we look at a place that's getting wetter, right? And we see that the GRACE data just go up and up and up and up. I would like to make the case here, and I've talked to Professor Tapley, who's the principal investigator, about making a bigger push to try to integrate these data into our national forecast systems, because there's a lot of information here. Let's look at Texas. When I gave my talk at Texas A&M, it was right here. Okay, it was right at this point, right at this lowest low, and everyone there, and even everything that I read at the time, said this drought, this is an 11-month drought. And so I pulled out the data, and I don't see an 11-month drought. I see a time history, a time series that shows a decrease over the whole time period that's shown in this chart. Okay? And likewise, we can look at a wet area, an area that might be flooding more, an area that might be flooding more in the future. And if I were a water manager and I were keeping track, again, this is showing us the total amount of water, say, in a river basin in upper Missouri. It's showing us that amount of water is going up and up and up every year. If I were a water manager, I would be anticipating floods. So I think you can see from some of these charts that there's a lot of information that's not being used by our forecast centers, and so that's something that we'll be pushing on. Let's look at our next clip.
Even during war, water committee used to meet.
Throughout the Intifada.
Okay. Yes. Throughout the Intifada, and even between the Jordanians and the Israelis before. So it's not that, if there is a conflict, there must be war over water, but you will see it the other way around. People meeting secretly to really solve their differences.
For instance, the Earth Middle East is the only regional organization, very sadly, that exists. There is no other organization that brings together Israelis, Palestinians, Jordanians as one organization in any field.
You will always have problems when you are living in a castle and your neighbor is in a cottage. When the Israelis enjoy waters 24/7 in Jordan, it's 1 day per week. And in Palestine, they'll be lucky if they get it 1 day per week.
هلا فهمتك بعض الناس فنيين أو خبراء من الأردن ومن إسرائيل اللي بيحاولوا يشتغلوا على قضية المي، أو شو رأيك؟
فيش حدا يكره فيه، ولما ينفع حربية ويزرع فلان الكل يستفيد يعني.
You cannot stop a bird from flying across a certain border. You cannot stop the water to flow, across borders.
The demise of the Jordan River is very much connected to the conflict.
So I've seen the movie 20 times, and I only slept through it once. There's a lot in the movie, and so one of the things that went by quickly that you may not have picked up was the line that said Israel enjoys water 24/7 and Jordan gets it 1 day a week, and Palestine will be lucky to have it 1 day a week. I mean, that's just, for us in the United States, that's unfathomable. Okay? But many parts of the world are experiencing that. So it's a real eye-opener. And so the question is that the Friends of the Earth are addressing is, can water be used rather than as a source of conflict, as a source for collaboration? And that's something that they're really promoting. I'll just show this figure again. I'm a little more skeptical, because I see that this big red blob here that represents groundwater depletion from our GRACE data sits over Turkey and Syria and Iraq and Iran. And I already mentioned that the amount of groundwater depletion was something like almost 100 cubic kilometers over a 7-year period. So I don't know. I think maybe I'm a little bit glum, not even delightfully glum. Let me show you an animation that's from the movie. It just kind of zooms in on this. So these are some of our data, and they were animated to show basically sort of this increasing red intensity, increasing red color, just increases in intensity. It shows how much water is being depleted from the region. Not that at all. This. Oh, there's no music. Oh, I'll add the soundtrack. No, I won't. So these are our GRACE data, and we'll see them pop up here for that region. But it's not just Turkey and Syria and Iran, Iraq, but you'll see that red color swings right around along the coast into Israel and Jordan and Palestine, right along the Jordan River. So this increasing red color is really meant to depict the accumulated groundwater depletion over the time period. It's not as exciting without music. Let's see if I can speed this up for you. There we go. Yeah. Okay. We shouldn't be cheering for that. That's not good. But I mean, I think that really spells it out, right? You can see it's all over the upper Middle East and then swings right down into Israel and Jordan. It's quite scary. I want to shift into some more solution-oriented stuff. One of the things that I think, we have to consider all options. And one of the big options is this: toilets to tap, is recycling of sewage water. Just a show of hands, would you drink recycled sewage water? Who would drink it? You're all lying. I know, that was about 50%. You probably already are drinking recycled sewage water. You just don't realize it. I was in California. I didn't know it. And we have a state-of-the-art plant called the Groundwater Replenishment System in Fountain Valley, California. It's in Orange County. And this clip that I'm going to show you from Singapore, that facility, the new water facility, is a replica of the Orange County facility. Let's take a look at this.
We are just a little island, but very densely populated. In Singapore, no raw sewage or used water goes out into the sea. We recycle it, producing a product that we call new water. We don't even use the term sewage. We just tell them, it's used water.
That's called fraud.
The concern, of course, was how will people respond. And so we explain the technology behind your water with reverse osmosis. What you get It's practically distilled water. In solving the water problems, I think we have turned what has been a vulnerability, if you like, into a strength for Singapore. 30% of Singapore's water supply will come from new water.
That's going to be my Halloween costume. Okay, so that Singapore facility is based on this facility, the Groundwater Replenishment System in Fountain Valley, California. I love this place. I put it right up there with, and I'm not kidding, I put it up there with Disneyland in terms of tourist attractions. If you go, just go to the website, find out when the tours are, contact Jay, he'll contact me, I'll go with you. It's amazing. Let me show you a few pictures. It's a 3-stage process. Microfiltration takes out all the big stuff. And so here's Mike Marcus, the general manager. And those little strands there actually have tiny little holes, and the water's forced through the little holes in those little straws. And a lot of the big stuff is left behind. And so these tanks over here on the left are where all that's happening. Second process is reverse osmosis. The water is forced now through a film to remove the rest of the bad stuff. The film sort of looks like this. And these are some of my students on a field trip that we took. The third stage is the UV with hydrogen peroxide. So this water is super purified. I mean, and it does come straight from the sewage treatment. The sewage treatment plant is co-located with this groundwater replenishment facility. They're right next to each other. So they just pipe it right in. It's good. So yeah, UV with hydrogen peroxide really gets rid of the bacteria and blasts the rest of the stuff away. And then it's time to do, in post-treatment, to do the taste test. I want you to look at my face, okay? And just watch what happens as I'm getting ready to drink this stuff. I'm getting a little more skeptical. But everyone's laughing, we're all drinking it, and finally we've all had it. And it's, you know what? It's so clean that they actually have to add minerals back into it. We take that water and we inject it right back into our aquifer that underlies Orange County. We use about half of it as a barrier for seawater intrusion. We use the other half for drinking. We mix it right in, and it's good, man. It's good stuff. Okay, how can we convince people that recycling sewage is a good idea? Maybe we need a pitchman. Okay, I need to go out of my show here and get a YouTube video of our pitchman.
Love your family. You know what I love? This idea. I see the world, right?
And you're going to look like a super.
We're so excited you agreed to be the face of Porcelain Springs. By the way, can I get a bottle? Yeah, we'll just get you cold right now. Yes, please. All right.
Thank you. Cold one.
I can't wait to taste this stuff. Recycled water. I'm all about recycling. By the way, how is it exactly recycled? Yeah, skim it. Yeah.
It's kind of a skimming part of it, anyways. You know this whole like crazy water thing that's going on in the world, right? What they're doing is they're taking water from the gutters, from sewers, from your toilet, right? And then there's some sort of like scientific process, I don't know, above my head. I just work under you. Anyways, they are literally straining the poop juice right out of the water back into the so it's defecate, drinkate. This is good. This is green. This is like the future. The future's now.
It's not like you recycle your can. You pick up a walk in your can. I'm not backing out. Taking responsibility. So I have to do this. Okay? Let's save the world from thirst.
So Jack, we're going to see behind you parched landscape, post-apocalyptic.
Water world without water.
You got it.
For too long, we've taken water for granted. We've polluted our rivers and lakes. We left the tap on while brushing our teeth. There is no new water left. Water. But wait! There's one source left. One pure source of hope that springs eternally.
Oh man, I'm thirsty. Well, I think that seems like a pretty reasonable place to stop. I'd like to thank you all for coming. I encourage you to, the DVD comes out on November 6th, on DVD and Blu-ray. Thank you so much for coming, and have a wonderful night.
So we'll go right to questions. I'm sure Jay will be happy to answer questions. Have at it. So go ahead.
Sure.
Okay.
There must be some questions. Can you hear me okay if I mic up or do I need to say everything? I need the mic. I'll be back. So it's very hard for me to see you. I see that hand.
So you showed where water is going up north.
Yeah.
The more temperate areas are getting drier.
Yes.
So why couldn't we go ahead and build the shovel-ready jobs of canals to take water from north to south?
So I think these are things that we have to think about for the future. So I agree. I think the future will be defined by the haves, especially as we start moving out several decades. The water future will be defined by the haves and the have-nots, and I think we need to be thinking exactly about these sorts of things. Yes?
I noticed that Greenland and parts of Alaska are red. Does that mean they do not have groundwater?
That means that what that signal represents is the Greenland ice sheet melting away, and Antarctica is like that as well, and then Alaska, that's the glaciers. So that's what those signals represent.
Thank you. Let's ask people to come down to the mic.
Okay. Yeah, if you have a question, come down to the microphone. And then we can't forget our webcast friends, right? Yes, sir.
Will recycling water through sewage be enough to stop this disaster that seems to be looming?
No, I think we need really a portfolio of approaches, and the portfolio should include many things: conservation, increased efficiency, recycling. Some places actually desal will actually work and will be important. Some places it won't. So I don't think there's any one silver bullet. Yes, sir.
I've read recently that about 10 or 15 years ago, a majority of the people in the United States were aware and believed in climate change, and now it's it's just a shrinking because of the massive attempt to debunk it.
Sure.
What kinds of hope do we have with this type of money behind the debunking of climate change?
Climate change? What are you talking about? So that's an excellent question. I was talking with a number of students about that today. So what this gentleman was talking about was really the climate deniers. They're extremely organized. They're funded by oil lobbies. They're quite a force, and they're a force that we're really, as scientists, not equipped to really fight. The good thing about water is that a lot of what's happening, it's much more clear. Right? We see the subsidence in California. You saw the picture, right? The wells are going dry. The water is contaminated. So we see that. So with respect to water, we had a huge drought, right? I mean, some of the towns here in Texas ran out of water. So that is undeniable. We're on a little bit better footing. We don't have to get into a climate change fight because the situation really speaks for itself.
Jay, we have actually some questions from the internet, so we'll come back to you in a minute. And so this comes from Region 15, from Cynthia Holcomb, one of the teachers up there watching the live webcast. Hi, Cynthia. The question is, what does the reduction of ice around Greenland mean for the USA in terms of climate change?
That's a great question, Cynthia. One of the things that's going to happen, the reduction of ice around Greenland will lead to sea level rise, and much of that sea level rise will have an important regional effect on North America, including the United States. So it's something that we really need to keep an eye on.
I hear a lot about people flushing medications and drugs, and it goes into the water supply.
Yes.
Does this water treatment plant take care of that?
So the one that I showed does. I don't remember what the water quality situation was like here in Austin. Pharmaceuticals are very important emerging contaminant. If you have any, so you can check with your local water district. But if you have any concerns, activated charcoal filters work great. They remove a lot of the pharmaceuticals. Yes, sir.
Okay, so I guess this question is actually more to respond to my dad's question. I was explaining to him how important water is and stuff.
Okay, so is your dad here?
I don't think so. No,
All right.
He's not. He's definitely not.
Okay.
But he basically replied that there's a fixed amount of water on the earth that it's not changing. It's not, but it cycles naturally.
Yeah.
And I guess I was just like, yeah, I guess you're right. But how would you explain to him that? I guess that it's not cycling, and I don't know. What would you, I guess?
Sure.
Say to him?
Okay. So I mean, there's many issues there, and one is that we're not creating or destroying water, right? We're just moving it around from mid latitudes to high and low latitudes, from the ice sheets into the ocean, from the land into the ocean and back again. So it's always moving around. Mm-hmm. The problem for us as humans is we're living in where a lot of those red spots were, and that's why the red spots are there. We like to live in dry regions. We like to live in Phoenix. We like to live in Southern California. I lived in Tucson. So we like to live in places that are dry. So then we're going to have to move the water from where it is to where it is not, and there are going to be interstate challenges, and there are going to be international challenges associated with that.
Thanks.
Sure. Yes, sir.
Hi there. I was wondering if your mass balance equation accounted for the withdrawal of oil, natural gas, places like the Middle East.
Yeah, so that's a great question. So we make the assumption that most of the mass changes that we see are related to water, and not things like oil extraction and erosion or changes of vegetation and so on. And so the actual minerals from mineral mining. And so we've done the math, and those terms are all second order. They really are. So water is super heavy and it's ubiquitous, whereas oil is concentrated. Water is everywhere. If oil were everywhere, we wouldn't have many energy problems.
I wonder if you could talk about the darkest red areas in the southeast. My previous understanding was that shortages were happening in Tucson or Las Vegas or the Valley or Phoenix. But why do we see that those areas seem generally
Yeah.
green or yellow, but the
Sure.
darkest red is in.
Yeah, so the southeastern U.S. Has just been experiencing a tremendous drought over the time period of the GRACE data, so since 2000 and since 2002. So one of the things, so that signal really represents a combined signal of the drought and then the human response to the drought, which is to use more groundwater. So that's what's happening there. So it's like a 2-for-1. You've got the drought, and so you're not getting as much rainfall, and then because it's a drought, you're using more groundwater. So that's what's happening.
Thanks.
Sure.
So it was mentioned in one of the clips that the water cycle is changing, therefore becoming more drastic.
Yeah.
Why? Why are some places experiencing more intense weather?
So a lot of it has to do with greenhouse warming and the fact that the atmosphere can hold more water. If it can hold more water, we can get more evaporation. If there's more evaporation, we can get more precipitation. So most of it has to do with the greenhouse forcing, and then some of the changes in the atmospheric circulation that are a result of that and necessary for the Earth as a system, without sounding too technical. It has to redistribute this extra energy. And so part of the way that it's doing that is by moving more water around, and as you move more water around, there's more energy used and more energy released, which results in more drought and more severe precipitation.
Thank you.
Sure.
Okay, Jay, let's jump in and take another question from the internet. This question says, so, excuse me, are we currently drinking poop water? If so, are they using the same process as the people in Singapore? I guess you could answer for Los Angeles.
Okay, yeah. So I am currently drinking poop water, and I don't know if you are or not. Jay, do you know if there? I don't think there's any major recycling. I think you would know.
There's no co-location like that.
Right.
Upstream users.
Sure. Right. I think. Right. And so I think a lot of people forget that with surface water, it's used many times, and sewage water is treated and put back into the river. So I don't see your name, but although you don't realize it, you're drinking poop water too. Yes, sir.
Most of what you were talking about today was over land and the groundwater in the land. Is there a difference between land-based analysis and what you get over the ocean, seafloor?
So a difference in what? I guess I don't understand the question.
I wonder if the analysis of the density, the gravity anomalies are
right.
different.
So we see different things. Yeah, I mean it's basically the same. It's the same stuff. What we see what we're able to see in the ocean is actually quite important. We can see the mass change part of sea level rise. So when you combine that, we have other satellites called altimeters that show us how much sea level is rising. Sea level rise is a combination of both the increase of water, mass change, and the fact that water expands as it gets warmer. We call that thermal expansion. So having the GRACE data allows us to see the mass change part of it. And a lot of that's due to the melting ice sheets right now.
Do you know how much a gallon of that clean blackjack pea water costs?
It was actually free for a while. I have some in my garage. If you give me your address, I'll mail you a bottle.
My question is a little more direct.
Yeah.
What is the processing cost for a gallon of recycled water?
So I don't know.
Processing cost, also the energy. What kind of energy consumption does it take in order to process?
So all I can say is that and I don't know the answers, and it is not it's not as energy intensive and not as expensive as desal, but of course it's way more expensive than conservation and efficiency. So I don't know the answer, but you know the cost will come down as the materials used in the membranes as better materials are developed that require less energy to push the water through.
In the IPCC projections map that you showed, it suggested that there's going to be increased precipitation at very high latitudes, if I recall, which presumably those latitudes would be more snowfall. And yet we're seeing reductions in ice layers and sea ice. It seems to be a conflict there. Could you
Right.
give an
So,
opinion?
no, it probably won't be more snowfall up north. There will probably be more rain. It probably would be more liquid precipitation. So that would be consistent with melting sea ice.
So the rain would actually help to melt what
It could,
snow and ice.
sure. Yeah. Yeah.
Thank you.
Yes, young man. I think you need some help.
Thank you. Couldn't the clouds move from the south, taking the evaporated water from the south, up to the north where there's a lot of blue spots, which means a lot of water?
Dude. Why didn't I think of that? That's a good idea. So really what you're talking about is trying to move the clouds and sort of affect... You know what? What you're really talking about is something that we call weather modification. And if we could really modify the weather, we can't. But if we could, we would not really be having any problems. We'd be generating rain where and when we wanted it and when we needed it. So it's a great idea. I wish we could pull it off. But we can't. And you should apply to be a graduate student in my program. Thank you.
Since an alternative source of power is water for things like oil and natural gas, and essentially right now we can't supply ourselves with enough water, do you think in the future we'll use water to power things like electricity?
So that's going to be a challenge. I mean, we use a lot of hydropower right now. So there's really two parts of the question. One is that we actually use a lot of water to generate regular coal-fired power plants, and so this is an issue. We use a lot. And it changes the temperature, it affects the ecology, so there are some issues there. The issue with hydropower, so hydropower is a great renewable, and maybe it's going to be the kind of thing that will work at these high latitudes where we have more precipitation. Where we use a lot of it right now, like in California or around the Himalayas, those are places where actually the snow is disappearing. And it's the snow melt that drives the hydropower. So we have a lot of hydropower in the western U.S. So with no snow, we really have to keep an eye on whether we're going to get more liquid precipitation or whether the region will just become drier, which is actually the prediction, and whether hydropower will actually be viable for us in the future. It might not.
Thank you.
Hey, I'm sure Jay would be happy to answer some questions one-on-one for a little while, but for now, let's thank him for his exciting talk. Thanks for doing it.
Yeah, my pleasure.